Okay, so in the next few videos, we'll be developing the required machinery in order to generalize our earlier observations into higher dimensions. And namely, that'll require understanding what are the so-called differential K-forms. And differential K-forms, I feel like, are something which are often just sort of thrown in as a definition and not really explained too deeply as to what they mean. So I'm going to go slowly and try to explain each step of the abstraction from starting off with simple geometry to ending up at differential K-forms. Okay, so I'll start off by working just with vector spaces and talking about K-forms there. And then we'll add geometry to it, and then eventually we'll talk about the exterior derivative, which will generalize our gradient integral and whatnot. So let's review what we went over last time, which was that we collected our earlier observations into two uniform sort of looking things. So in R2, we have the sequence of C infinity functions and vector fields related by these differential operators, and same thing in R3. And we notice that C infinity functions and vector fields form vector spaces in their own right. And in that point of view, these differential operators are linear maps. And so we define these cohomology groups, H0 as being the kernel of the gradient, H1 as being the kernel of the curl modulo the image of the gradient, and H2 as the kernel of the divergence modulo the image of the curl. And we notice that H0 corresponds to codimension 1 holes, H1 corresponds to codimension 2 holes, and H2 corresponds to codimension 3 holes. So to put that into a bit more concrete language, for example, if we look at H1, then we can find some function which has 0 curl and ask if it's the gradient of some function. And if we can find some function which has 0 curl but is not the gradient of something, then we saw that the only way that that's possible is if there is some sort of a hole in our space. And so the function forms a non-trivial element of this quotient space because it's something which is in here but not in here. And so it sort of adds to the dimension of H1. So these should be the dimension of all of these. And so it corresponds to some sort of a codimension 2 hole in our space. And so this is something that's quite profound because it says that if you want to understand the topology of your space, then you can try and understand the sort of functions or vector fields defined on your space and look at how they interact with each other. And on the other hand, if you're more interested in the functions of your space, for example, if you want to find a sort of potential function for a vector field, then there's sort of a calculus obstruction, which is to say that the curl has to be 0. But if the curl is equal to 0, you're almost guaranteed to be the gradient of a function, so long as there's no holes in your space. And even if there are holes, we showed that using Stokes' formula, so long as you get 0 along every loop integral, you can still end up as the gradient of some function. Okay, so these are very nice, and it's quite uniform between both cases. And usually in math, when you have something which is nice and only works for a small number of cases, like 2 and 3 dimensions, that's usually a smaller part of a bigger picture. And our goal now will be to generalize these things to higher dimensions in order to see what sort of interesting statements we can come up with there. So if we try looking at something like R4, we can try generalizing these sequences and see what something that we would get. And so maybe our guess would be something like C infinity, and then maybe we have like vector fields in the middle. And then some differential operators in between them. And so maybe you might just guess vector fields because over here there's 1 vector field, here there's 2 vector fields, so here there must be 3 vector fields. And then this will sort of correspond to H0, this will correspond to H1, H2, H3, and maybe H4 as well. And now we just need the differential operators relating the two. So these are our vector spaces, and we need some linear maps between them. And so the first one should be pretty clear, it should be the gradient, because the gradient works in these two cases, and it also generalizes pretty easy to R4. You just take the derivative with respect to each of the 4 basis vectors, or each of the 4 directions. However, the second one is a bit difficult to generalize, and the point is really that we're used to the curl in terms of 3 dimensions. And so I call this the curl for a good reason, but really the curl is a 3-dimensional concept. And the way that works is it uses the cross product. So you take the cross product of the del vector, which is sort of the vector of the derivatives, and the 3 different functions that you have, and this is the curl of this vector field. And so because the curl uses the cross product, and the cross product only works in 3 dimensions, it doesn't easily generalize to something which should go over here. relating vector fields to vector fields. But the good news is that the fact that it does involve the cross product is actually your first hint of how to properly generalize it. So it turns out that the cross product is something which usually you think of as taking in two vectors and spitting out another vector. But really what it's doing is it's taking in two vectors and giving you something which is related to an area. And so you're already familiar with this because when you try to compute the area spanned by two vectors, then you take the cross product and look at the magnitude of it, and that'll give you the area of the parallelogram spanned by those two. But it's actually even stronger than that, which basically anywhere in physics where you see a cross product, it's always something involving areas. So for example, torque, sure you can say you're rotating around this axis, what you're really saying is you're rotating in that plane. And even the magnetic field, which involves some cross products, can be better interpreted as something to do with areas. But that's a story for another time. Now the reason that the cross product only works in 3 dimensions is because we can sort of cheat and talk about areas in terms of vectors. And why is that? Well, it's because every plane has a unique perpendicular vector. So if we have some area in this plane with a specified area, we can cheat and talk about the vector that's perpendicular to it with the same specified area. But in higher dimensions, this doesn't quite work out because to every plane there isn't a unique perpendicular vector, because sort of the dimension count doesn't work. In 3 dimensions, 2 plus 1 equals 3, but in 4 dimensions, it'd be 2 plus 1 still equals 3, but that's less than 4. However, you still have a notion of like 2-dimensional things in 4 dimensions, and so it still makes sense to talk about areas, and so that's what we'll be focusing on. So the fact that the cross product sort of represents areas is our first hint that we should, instead of looking at vector fields here, be looking at something to do with areas. Another hint is that a vector field is kind of like a collection of 3 different functions. But the infinity functions are just one function. And so we can actually explain this if we look in terms of areas, which is to say that the second column sort of represents the space of areas in our space. So in R3, there's sort of a 3-dimensional space of areas, basically because each area has a perpendicular vector. And because there's a 3-dimensional space of vectors to play around with, there's also a 3-dimensional space of areas to play around with. However, in 2 dimensions, we're stuck to only working in one plane. And so there's only one area to work with. And so that's why here we have only one function, whereas here we have 3 different functions. And a third reason why we want to look at areas instead of vector fields, or why it's more natural to, is because we've been using Stokes' theorem a lot, which says that the integral of f over the boundary of some surface is equal to the double integral of the curl of f dot dA over the interior of that surface. And so the idea in properly generalizing the Rham cohomology, which are these things over here, is that we shouldn't be looking at just the expression f and just the expression curl of f, but instead be looking at this whole expression and this whole expression. And so using some change of coordinates, you can express any integral dA as being like an integral of something dx dy plus dy dz plus dx dz. And what you're doing here is sort of like here you're integrating dx plus dy plus dz, and so you're integrating infinitesimal segments together. And over here you're sort of adding up infinitesimal areas together. And again, the fact that there's 3 of these guys, this one corresponds to the xy plane, the next one corresponds to the yz plane, the next one corresponds to the xz plane. Again, hints towards the fact that there's sort of 3 dimensions of areas to work around with. And so all these put together tell us that in order to generalize this to higher dimensions and other scenarios, we shouldn't be looking at the infinity functions or vector fields in this case, but we should be looking at something which has to do with areas. And so our next goal will be how to describe areas in a proper fashion in order to talk about them in the same language. Okay, so hopefully now I've convinced you that if we want to be able to generalize our remarks to higher dimensions, then trying to understand how to describe areas is the right thing to do. And we'll start off slow by working only in vector spaces and doing things linear algebraically, and then we'll slowly add in the calculus. But, so what do we want our area things to satisfy? Well, we want them to be similar to vectors, and vectors can be described as things which have a magnitude and a direction. And similarly, we can describe an area as something which has a magnitude, which sort of describes the area of some shape, and an orientation, which in 3 dimensions is sort of like what plane the area lies in. And moreover, we want this something to do with areas to replace our second vector fields thing, so that our curl can go from vector fields to something to do with areas. And we really use the fact that vector fields in 3 dimensions or C infinity functions in 2 dimensions form a vector space. So we also want these area things to form a vector space, and so that'll look something like the scalar multiplication will be given by, if you have something with area A, then you can scale it up by a factor of 2 or by a factor of a half or by a factor of pi, and then you'll get something with an area of 2 or a half or pi. And so I'm saying scaling isn't like scaling in just one direction. And addition will be given by, say you have something with an area of A and something with an area of B, well, you put them next to each other and then you have something with an area of A plus B. So that'll sort of give a natural vector space structure on our set of all area elements, as I'll call them. Okay, so we're going to be starting off with just vector spaces, and the simplest sort of vector space, which will be R2, or the simplest vector space which we can talk about areas reasonably. And so in R2, we only have one plane of areas to work with, and so we won't see much of an orientation come into play, but we will see a distinction between positive and negative orientation. And this is similar to how if you have a one-dimensional vector space, there isn't much to talk about directions, but you still do have if two things are pointing in the same direction or if two things are pointing in opposite directions. And then when we generalize to 3 dimensions, we will be able to see that orientation plays a bigger role by talking about sort of what plane the area lies in. Okay, so now we want to describe these area elements as things with some sort of magnitude, which is mostly what we're focusing on because there's not much of an orientation to worry about. But how should we describe them? Well, since we want to stick within the realm of linear algebra, we don't have many shapes to play with. We don't have like circles or ellipses because they're not, well, linear. But we do have parallelograms. So we can describe areas in terms of parallelograms and say that some parallelogram with an area A will describe an area element with the specified area. Now in linear algebra, we don't have much of a good language to talk about parallelograms, but we do have a good language to talk about vectors. And we know that any parallelogram can be spanned by two vectors, v1 and v2. So we can describe this area element as being the pair v1 comma v2, where v1 and v2 span this parallelogram with an area A. And so this gives us a preliminary definition of an area element, which the set of all area elements is the set of pairs v1 comma v2, such that vi, so v1 and v2 are in our vector space V, and in this case we're only working with v equals r2. And so you should think about this as you giving a pair of vectors, and you should consider the parallelogram that's spanned by them, and then this pair of vectors represents the area, which is the area of the parallelogram spanned by them. And okay, so now we have a description of what this looks like, and we want to describe scalar multiplication and addition on it. But even before we do that, there's a bit too much information going on here, because all we care about really is the area of the shape, and not really, well, the shape of the parallelogram. So if you keep track of the two vectors, that'll tell us the shape of the parallelogram. But for example, if we draw another guy, which has the same area but looks different, we want to consider these two to be the same area element, because they have, well, the same area. And this is similar to probably when you first learn linear algebra, they tell you that vectors can be put in different points in space. But it doesn't really matter where in space they're put. All you care about is the magnitude and the direction. And similarly here, all we care about is the total area of the shape. We don't really care about the shape of the shape itself. And so what we're really going to do is say this one is spanned by two vectors v1 prime and v2 prime. We'll come up with an equivalence relation, which is to say that we'll consider v1, v2 to be the same as v1 prime, v2 prime for all intents and purposes, if the parallelograms spanned by these two have the same area. So now the question is, how can we determine the area of a given parallelogram? And once we determine the area of a given parallelogram, then we can say that two pairs of vectors are to be considered equivalent if and only if they generate a parallelogram with the same area. Okay, so if we have some parallelograms spanned by the vectors v1 and v2, then you probably already know how to compute the area of this parallelogram. But instead of jumping straight to the final answer, we're going to systematically break it down and sort of do some geometric processes to reduce the parallelogram to a simpler shape that we can compute. And the reason for doing this is that we'll see that the steps involved in simplifying the shape geometrically and then reverse engineering the area will actually give us the necessary axioms in order to have a better definition for our space of area elements. Okay, so if we start with a random parallelogram, it might not be clear to us how to compute the area beforehand, but there is a special type of parallelogram which we do know how to compute the area of, and that is a rectangle. So the question is, can we reduce any parallelogram to a rectangle? And then once we do that, we can just compute the area of the rectangle and say that these two, and try and figure out the area of this from there. And so the answer is yes. And one way to see this is usually the first place that you derive the area of a parallelogram is sort of like a slanted rectangle like this. And what's going on here is you're replacing this vertical vector with this slightly slanted vector and changing to this parallelogram. But if you look at the area of the rectangle, it's just a bunch of these horizontal segments, and the horizontal segments are basically the same thing here, except it's just sheared a little bit to the right. And similarly, you can shear in the other direction, and you'll get something which looks like this. And now you can look at the vertical sort of slabs, and these will be preserved under the slanting, and so these two also have the same area. So the point is that if you shear your rectangle in either this direction or this direction, then you can end up with parallelograms with either one horizontal side or one vertical side, which will have the same area. And sort of going the opposite direction, if you started with this and you sheared it the other way, then you'll end up with the rectangle. Now the thing is, it doesn't really matter that we start off with the rectangle. We could have started with any parallelogram. And what we can do is we can shear the second vector in the direction of the first vector. So what that means is send the second vector to any vector that lies along this line. So we can choose this vector, which will lead to a parallelogram that looks like this, or we can choose a vector that looks like this, and then that'll lead to a parallelogram like that. And all these have the same area, again, because you can sort of look at horizontal pieces, and those will sort of just slide around. And so the point is that this parallelogram will have the same area as this one. And we can choose a particularly nice parallelogram, which is if the second vector points vertically. And you can convince yourself that there is one and only one such sheared parallelogram which satisfies this. And so this will allow us to change our initial parallelogram into something which looks like this. This will be like V1, and this will be V2 prime, which is V2 plus alpha V1. And it's alpha V1 because basically it's the amount that we've translated along this line. So this vector would be alpha V1, and if you add up these two, then you get V2 prime. And then you can shear the second part horizontally down to get V1 prime is equal to V1 plus alpha V2 prime, or I guess beta V2 prime. And this was just saying, okay, we can do the same shearing process and shear down vertically here to get some vector V1 prime, which will make our parallelogram into a rectangle. And so our end result is a rectangle like this, which has the same area as this initial parallelogram that we started with. Okay, so this composes our first axiom, which I will call the shearing axiom. And this says that if you take any pair of vectors v comma w, this is to be equivalent to v comma w plus alpha v, and also equivalent to v plus alpha w comma w. And so what this is saying is that you start with the two vectors v and w, and you can either shear v in the direction of w and move along this way, or you can shear w in the direction of v and move the second one along this way, and the resulting parallelogram will have the same area as the original. And this allows us to reduce our parallelogram into a rectangle. And so now if our rectangle, spanned by say v1 and v2 again, has side lengths a and b, then we know that the area of this will be ab. However, we can do further reductions in order to get down to something even more fundamental. And so the reason for this is that we want to sort of minimize the amount of formulas that we use and try and do as much geometry as possible instead of as much algebra as possible. So what we can do is we say, okay, rectangles are nice, but there is a very special rectangle, which is arguably the nicest, and that is the unit square. And so this is spanned by the vectors 1, 0 and 0, 1. And so I'll call these vectors E1 and E2. And we can say, okay, how can we relate this rectangle to this? Well, we can scale E1 by a factor of A horizontally. This will be A, E1, and E2. And this will have an area of A if this guy, the only natural area to put is 1. And this guy will have an area of A. And then you can scale this E2 vertically. And then you'll end up with the original rectangle with A, E1, B, E2, which is what we started with. And scaling vertically will also scale by whatever scale factor we put on the side. And so this will have an area of AB. So what this means is that instead of directly saying that the area of a rectangle is AB, we could say, okay, start off with the unit square, declare that the unit square has an area of 1, and then scale in each direction in order to deduce that the area of the rectangle has an area of AB. So this is what I'll call the scaling axiom. And this I'll say that alpha times VW is equivalent to alpha V comma W is equivalent to V comma alpha W. And so what this is saying is you can sort of scale in the direction of one vector, and that'll scale your area by the same quantity. Or you can scale by the direction of the other vector, and that'll scale your area by the same quantity. And you can convince yourself that the same thing works for general parallelograms instead of just like rectangles. And so you should be a bit annoyed right now because these two are well defined because we defined our area elements as pairs of vectors, and alpha V and alpha W are still vectors. But this, as I've written it, is currently undefined because this is some sort of an area, but I haven't told you what some number of times an area is supposed to be. But as I said earlier, this should be some sort of a figure which has an area of alpha times the area of this parallelogram. And so what we're declaring is that the parallelogram spanned by these two vectors has an area of alpha times the area spanned of the parallelogram spanned by these two vectors. And this is essentially how we'll define this notation, and it's sort of hinting at the fact that this is how we have scalar multiplication on our vector space. And finally, we need one more axiom, which is that the area of this guy is equal to 1. And so I'll call this the special area axiom, and I'll say that the area of the pair E1, E2 is equal to 1. And the reason that we need to add this as an axiom is because we just chose basically a basis for a vector space. And you could say, okay, this has an area of 1, but you could also assign it different areas. For example, if someone else measures in inches and I measure in centimeters, then this could have an area of 1 square centimeter for me, and it'll have a different value for them. But the thing is that if I draw something with like 5 times the area of this, then regardless of if I say this area is 1 or if this area is 7, that other thing will have an area of 5 times the original one. And so this special area is really a separate statement than the other two, in that you're just choosing a special parallelogram or a square and declaring that its area is 1. And another way to see why this is not unique is because, as I said, this is like a special choice of basis. And you can choose another arbitrary pair of basis vectors and express everything in terms of that basis, and then you can say, okay, well now that's 1, 0, and 0, 1, and so that'll have an area of 1. So we'll worry about this one later, but the point for now is just that we need to declare that the area of the unit square is 1. So I claim that this is enough to be able to deduce the area of any parallelogram, and I should probably go ahead and show that. So let's say that we have a pair, B1 is equal to AB, and B2 is equal to CD. And what we want to do is compute the area of the pair AB, comma, CD. Okay, so the first thing we want to do is use the shearing to get ourselves down to a rectangle. So we should shear V2 in this direction to get a vector which is vertical. And so I'll call this v2 prime, which is v2 plus alpha v1. Okay, and so what will this look like? So v2 prime is equal to ab times alpha plus cd. And this should be something that's vertical. So the second component of v2 should be, well, it's arbitrary, but the first component should be 0 because there's no horizontal displacement. And so what this tells us is that alpha a plus c and alpha b plus d is equal to 0 and something. So from this we see that alpha must be equal to minus c over a. That is how much we are displacing in the direction of v1. And then we get that the expression for the second component is d minus bc over a. And so what we get is from the shearing axiom applied to the first component, that, or the second component actually, is that this is equivalent to ab comma 0 d minus bc over a. Okay. Now we have reduced this from the slanted parallelogram to something with a vertical vector and something with a slant. And again, now we just want to shear in the second direction and get something that is horizontal. So this is v1, this is v2 prime, and what we want to get is v1 prime, which is v1 plus, I guess, beta times v2. So how can we compute this? Well, again, v1 prime is equal to ab plus alpha times 0 d minus bc over a. And this will be equal to something and 0 in the second component because we want this to be horizontal, so it shouldn't have any vertical displacement. Okay. So you can see that there should be a value of beta here, and you can solve for it, but regardless, this entry is 0. So no matter what the value of beta is, we know that the first entry must be equal to a. And also implicitly in these steps, I'm assuming that you can divide by certain quantities. Sometimes you won't be able to, so I encourage you to think about geometrically what that will look like and verify that the same end formula will hold. But anyways, using the shearing axiom on the first vector, we get that this is now equivalent to the pair a0, comma 0 d minus bc over a. Okay. So now we have reduced ourselves to a rectangle, which looks like the following: v1 prime, v2 prime, which has the same area as our original thing. And so now we can say that this is equal to a e1 and d minus bc over a times e2, basically by the definitions of e1 and e2 as being 1, 0, and 0, 1. And now we can say, okay, using the scaling axiom, we can sort of shrink this by a factor of a in the first direction and gets e1 and v2 prime. And so this will be a, or equivalent to a times e1 d minus bc over a e2. And then we can shrink in the second direction and get e1 e2. And then we get that this is equivalent to a d minus bc over a times the pair e1 e2. And so now, using these axioms, we have reduced everything to ad minus bc times the pair e1 comma e2. So what this is saying is that the parallelogram spanned by the vectors which have these entries has the area ad minus bc times the pair of vectors spanned by these two vectors. And so remember, we declared that these two vectors span an area of 1, and so that implies that these two vectors span an area of ad minus bc. And that's where the usual formula for the determinant comes from. Okay, nice. So now we have a systematic way of computing the area of any parallelogram. What I want to note, sort of why I was emphasizing the special area earlier, is that we don't actually need to use a special area to compare two pairs of vectors. So remember, our original goal was to say, okay, when can we say that two vectors v1 and v2 are equivalent to v1 prime and v2 prime? And we say that these are equivalent if they generate parallelograms of the same area. Well, if I said that this had an area of 5, if we have two parallelograms which are both 3 times the area of this, then regardless of if I say this area is 5 or if this area is 3 or if this area is pi, those two other parallelograms will still have the same area. So you don't actually need this third special area axiom in order to identify two pairs of vectors together. And essentially what that boils down to is we now have a more refined definition for our area elements, which is the following. So the area elements are going to be pairs v comma w, where both of these are in our vector space. And again, right now our vector space is just R2, modulo shearing and scaling. And so again, we could add the special area axiom, but the special area axiom doesn't actually contribute to this equivalence relation at all. All it does is it tells us the area. We don't actually need to compute the area to say that two things have the same area. Okay. Yeah. So now, by our scaling axiom, we have a natural sort of sense of scalar multiplication on this. And that's the first step towards, as I said, making this into a vector space in its own right, where we can do scalar multiplication and addition. And addition is a bit weirder because we're defining these as just being pairs of vectors. And so if we have two parallelograms, say something which looks like this with an area of A and something which looks like this with an area of B, then we want to be able to add them together and get some sort of shape which has an area of A plus B. Alright, this is bad, but some sort of parallelogram which has an area of A plus B. And so there's no clear way of sort of sticking these next to each other in order to get a parallelogram of area A plus B. But the nice thing is that we're looking at not just pairs of vectors, but pairs of vectors up to equivalence. So we can change our first parallelogram into some other parallelogram which, say, has a width of A times E1 and a height of E2. And our second one we can change using shearing and scaling to get something which looks like B E1 and E2. So this will be represented by the pairs A E1 comma E2 plus B E1 comma E2. And there's a natural way to add these, which is just add the first two components. And so this will be A plus B E1 and E2. And so what this looks like geometrically is sort of just sticking these next to each other. And so it'll be just a long rectangle with A and B over here and a height of 1. And that obviously has an area of A plus B like we wanted. Okay, so the nice thing is that since we're working up to equivalence, we can sort of choose special representatives up to our choice, and then stick them next to each other if they share one of their side links. Now you could ask, like, what if we chose a different representative, like something that looks like this, which has an area of A, and this is some special vector, let's say V, and we chose another one which has an area of B. Let's draw this a bit differently. Say an area of B, but the second vector is still V. Well, you can still add these together, and we'll get a bigger rectangle. This one has an area of A, this one has an area of B, and this side length is still V. And so this will correspond to something comma V plus something comma V equals something plus something comma V. And you can ask, okay, are these two resulting things equivalent? So what we want is for the addition to be well defined, right? So we can choose this as a representative representing this area, and this as a representative representing this area, and same for these guys. And we can add them up to get seemingly two different figures, but basically two things are equivalent if and only if they have the same area. And since these two are always going to have an area of A plus B, since you're just sticking two things next to each other with areas A and B, we get that the addition is independent of what representatives we choose. So it's kind of an ad hoc way to describe addition, but it does work to give us a well-defined addition on this vector space, and so we have achieved our goal of getting a vector space of things which describe areas and which we're able to do addition and scalar multiplication on. Okay, so now I'll describe how areas are usually described, which is the following. So you take your vector space R2, and instead of considering these pairs of vectors up to shearing and scaling, you consider two other axioms. And so the axioms are bilinearity which is okay, so the bilinearity property says that these two pairs of vectors is equivalent to this expression, and these two pairs is equivalent to this expression. So what this is saying is that the parallelogram spanned by these two vectors is equal to the area of this parallelogram spanned by these two vectors times alpha, plus the area of these two, the parallelogram spanned by these two vectors times beta, and similarly for this expression. And the alternating property says that if you flip the two vectors, then you get a negative sign out front for the scalar multiplication. And so as an exercise, show that 1 and 2 put together is the same as shearing plus scaling. And so the first one, you can sort of try and geometrically interpret this, and then you should be able to get the answer. But the second one is a bit more strange. And sort of to give you an idea of what's going on, remember that if we start off with two vectors, v1 and v2, our sort of prescription for figuring out this area was to send v1 to the vector e1 and send v2 to the vector e2. Because we specified what the area of e1, e2 is, but we never specified what the area of e2, e1 is. And so then you might ask the question, okay, well, what if we started with v2 is equal to e2, and sorry, v2 equals e1, and v1 equals e2. So essentially now we want to use shearing and scaling to be able to get this picture down to this picture. In other words, make v1 become e1 and v2 become e2. So you want to switch these two vectors. And you can try your best with shearing and scaling, but you'll realize eventually that if you just scale by positive numbers, you can never get to this picture. However, what you could do is essentially apply rotation and send v2 to v2 prime and v1 to v1 prime. So that looks like this. And so the one way that you can do this is to apply 3 different shears. So I'll let you try and think about how that works so that it fits into the framework of these axioms and you don't need to include an axiom for rotation. But what happens here is v1 prime is now equal to negative e1 and v2 prime is equal to e2. And so what we find is that the pair e2 comma e1 is equivalent to the pair negative e1 comma e2. And the only natural thing to do for scalar multiplication here would be to multiply this whole expression by a negative sign. Negative e1 comma e2. And so this is essentially sort of a plus or minus sign for the orientation that I was talking about. You can't say definitively something which has a positive orientation and something which has a negative orientation. What you can say is you can declare something to have a positive orientation by declaring that its area is plus 1. And then what that means is that if you were to flip the pair and consider e1 first and then e2, then you would have a negative orientation, which means that the area would come out to be negative 1. Okay, and one final comment about this is why do we want these two axioms instead of these axioms? Well, the nice thing is that these axioms are much nicer algebraically than the algebraic expressions for these. And so although shearing and scaling is sort of geometrically motivated and geometrically gives you a nice way to compute any area, they're not algebraically very nice. And as I said, we want to sort of be able to do algebraic manipulations with these in order to work with cohomology. And so we'll generally be working with these axioms instead. So the way that people usually define area elements is by taking the pair v wedge w such that v and w again are in the vector space, modulo these axioms 1 and 2. And people usually write this as v wedge v, or sometimes as lambda 2v. Okay, and this is technically for this case of v is equal to r2. And again, so this is much nicer algebraically. And what do I mean by this pair v wedge w? V wedge w is just the pair v comma w that we have been working with earlier. So this sort of represents a parallelogram spanned by these two. Okay, so now we'll talk about 3 dimensions and higher dimensions and the subtleties that come with extending the notion of area to that, and move on from there.